Thank you very much for the introduction. Yes, so I'm presenting this on behalf of Yuyang and Yu, who unfortunately could not be here today. But just as a preface, I wasn't directly involved in this research, so I might not be able to answer all questions, but more than happy to move any questions on to the authors, whose notes will also be available last one. So this work is BMFT, achieving fairness via bias-based weight masking fine-tuning, which I will be exclusively referring to as BMFT. So the goal of this research is to improve the fairness of medical image classification networks without sacrificing their discriminative performance in the process. So a little bit of background first. I think everyone in this room is well aware that over the last 5 to 10 years, there have been a deluge of research that has indicated clinician level performance are better for deep learning models across a variety of medical imaging tasks. But these models have been shown to exhibit bias towards sensitive attributes that are present in the data. So this could be something as simple as skin tone or gender, but it can go as far as details of socioeconomic status. And a lot of this comes from, we assume, or think, imbalance in the training data of these networks. So this is a really critical issue because it can not just impact the robustness of the general stability of these models, which can then cause harm to patients once they're deployed, but it could also exacerbate existing social biases. It could erode trust between patients and the healthcare system. And it could also erode trust in clinicians and healthcare workers and AI. So I thought there was another slide between them, but I'll put that one. This approach is called BMFT, and this is a post-processing method. So it takes an already trained model and it attempts to de-bias it or remove the biases that it has learned from its training data. And it does this by specifically targeting the parameters of the network that have exhibited or have learned the bias in the training data and fine-tuning specifically those parameters. And the key here is that they're able to target specifically the bias, so they're able to maintain the causal features that the model has already learned during its training, which allows it to maintain its discriminative performance. These slides are much shorter than the ones that I was sent, so there are slides missing here, so I'm a little bit thrown off. So I'll walk you through the mask generation process first. So the way that this method effectively works is they generate a mask to identify the parameters of the model that have contributed the most towards the bias. And the way that they do that is by using binary cross entropy during their training alongside a customized bias loss or bias term, which effectively measures how much a sensitive attribute from the data set, in this case it would either be skin tone or gender, has contributed towards the prediction that the model has made. And by taking that bias loss term and computing the second derivative of that, they're able to analyze the sensitivity of the parameters in the network. Specifically, what that means is they can see how important each parameter of the network was for predictions that are highly influenced by the bias attribute. And by doing that, they're able to acquire a mask of their neural network parameters, and they freeze the parameters that are not contributing to the bias, and then they perform fine-tuning specifically on the parameters that they've identified as contributing highly to the bias of the network. Once they've done that, they undergo a process that's termed impair-repair, which effectively is a fine-tuning process. They fine-tune their networks and then they reinitialize the entire classification layer and they perform fine-tuning on the classification layer. And they test this method by training on the ISIC skin lesion dataset, and then they perform their analysis on 4 different test datasets from 4 different skin lesion datasets. That includes Fitzpatrick 17, DDI, and Atlas. And these datasets exhibit or contain sensitive attributes such as skin tone on the Fitzpatrick scale and gender as well. So what they find when they compare BMFT to both their baseline, which is just trained using ERM, and 3 other fine-tuning methods and a pruning method specifically designed for fairness, they found that they are consistently across their data sets and across their different sensitive attributes are able to outperform both in terms of fairness, which they've measured through equalized odds, and in terms of discriminative performance, which they measure through AUC and through accuracy. So this is critical in that they're able to achieve far better trade-off in terms of discriminative performance and fairness than any other of the state-of-the-art that is most closely related to this method. Yeah, so to conclude, the BMFT constitutes a novel method to fine-tune an already trained model that's exhibiting biases, to remove biases in that data without negatively impacting the discriminative performance of the network. And what's key to this is actually they often improve the discriminative performance, which is very important. So yeah, thank you very much for your attention. I would happily direct you towards my colleagues and the first authors. Their emails are available on the slide, as well as links to the code and our labs page. Thank you.
Question.
Yeah, so all of the models that they use in the paper are ResNet models. They all come from the ResNet family. So it's ResNet 1834. Yeah.
That's exactly to my next question, which is scalability, right? If you then use models that have related parameters, for example, complex, yeah, how does this scale with that if you perform a fine-tuning during inference?
I'm going to need to direct that question maybe towards the authors. I'm not sure. I don't know if they've done any experiments investigating the difference in terms of their smaller models versus their larger models. They might be able to answer that question. Thank you.